Okay, cool. Hi, everyone. We're going to get started. Can I actually ask the people that are sitting in the back to come move up to the front? I would greatly appreciate that. Thank you. Okay, so I'll start with the obvious. I am not Sylvia. My name is Alex. I'm one of your TAs. And for the second flipped lecture, the TAs got together and we thought it would be nice to give you a lecture from the perspective of someone who took the class recently and went through the material recently and talk through some of the things that we found confusing when we were learning this material not too long ago. So, yes. This lecture was prepared by me, Narek, and Sarah, so two other TAs. I happened to take 168 here some years back, and they took the equivalent at their undergrad institutions, and so that's what we're basing our content on. So I'll start with some announcements. One, starting this week, in-person lectures are back. So no more videos to watch before coming to lecture. And Sylvia will be lecturing. Me being up here is a fluke, just for today. And two, the other really exciting announcement is that Project 1 is released today, immediately after lecture. And I'll share some more information about this project. You're going to be implementing a distance vector routing protocol. And in particular, what makes this really fun, why I like this project so much, is you'll be working with a simulator that Murphy McCauley and past grad students in NetSys have written, where you'll actually be able to see exactly what is happening in the network. So I have a little video from when I was working on this project over the weekend. It's very fun. The simulator is all jiggly. You can move all the nodes around. You can see all the packets as they flow. You can send packets from some host to another host. And you're going to be responsible for building the routing tables to make an arbitrary network function, which is really cool. So the project is split and scored by 10 stages, and the goal is going to be effectively to derive each of the changes that we learn to distance vector, optimizations to distance vector, starting from just basic packet forwarding and then understanding why we need things like split horizon, poison reverse, route poisoning, et cetera. It's going to be due at midnight on October 7th. And all of the information is going to be on ED at 12:30, immediately after lecture. Okay? And as people come in, just if you can come and sit in the front, that would be great. Thank you. I'll just also give a shout out here to Silvery, Tenzin, and Ken, who are the project TAs for this project. And they've been working really hard to get this ready for you and to get it released. And they will be the ones supporting you. So this is important. If you have questions while you're working on the project, come to project office hours, not the content office hours. So they specifically have lots of project office hours to get help. Are there any questions about this project release? No. Cool. I'm actually going to start with a few tips briefly that you should think back to as you start working on the project, just because I was just working on this project and from when I took it in the past. Given that the project is made up of these stages, later stages are going to require you to go back and edit your earlier code. So I highly recommend that you comment your code in the earlier stages because you'll have to go back and edit it. And very quickly we forget what our code does, even though we just wrote it. Very handy. Remember that when a node receives an update, if you are told that your neighbor has a path to some destination with some cost x, your path to that destination, if you choose to use that route, is x plus your distance to that neighbor. So you have to keep track of, you take however far your neighbor is from the destination and add your own distance to that neighbor to get the total cost that you store. And that was just something that bit me when I was working on this. And a higher level comment to say that this class doesn't have that many assignments, right? We have 2 projects, one kind of homeworkish thing that'll happen later in the semester, and 2 exams. And so this is your chance to really get very comfortable with these concepts of split horizon, poison reverse, and route poisoning, and how distance vector works. Because when it comes time for the exam, that's where we're going to apply these concepts and kind of stretch them more. And so really make sure for each of the parts you understand why what's happening is happening. And if you just follow the PDF, the instructions, it has questions to help you understand, as long as you make sure you're taking the time to answer those questions for yourself. Something that helped me do this is when I was thinking through things, I logged what was happening. So whenever I was writing an update to my table, the routing table, I would log that I was doing that, and then I could really look at the sequence of events and try to understand why the sequence was what it was. So And my last tip for you is that the simulator is a Python terminal. It's interactive. And so actually, while the simulator is running, while you have that little visual section, you can also refer to each of the nodes by their actual names, like S1, and view the routing table live. You can do print s1.table, and it'll show you the exact innards of your routing table. So that's really handy for debugging what's going wrong. OK. If there aren't any questions about the project, then I will get started on the section of lecture, what I found confusing about routing, and hopefully how we can clear it up. OK? So every semester, students get confused about this. They get confused about all these new terms, split horizon, route poisoning, poison reverse. And in particular, I see these questions very frequently. People ask, what combinations can you use? Which one of these three is the best? What is route poisoning versus poison reverse? The naming, the fact that it's so similar, doesn't help. Of course, even within split horizon versus poison reverse, what are their differences? So let's take the time today to clear those up. I'm going to set the stage first to remind you, this has already been talked about in lecture, but why are we doing this in the first place? So the core problem that we're trying to solve with routing is coming up with the rules for how we're going to forward packets. So as a router, you get a packet, you look at the header, and your job is to decide, to get this packet to where it needs to go, what do I do with it? Which neighbor do I give it to? Routing as a problem is how you come up with those rules, so that the actual decision-making process of who I should give this packet to, defining how you make that decision. And you have to make these decisions with some sort of requirements in mind. In particular, two very reasonable requirements. You probably want full connectivity, meaning that as long as a host is part of this core connected component of the graph, as long as it's theoretically reachable, it should be practically reachable from any part of the network. And two, you probably want to minimize latency. So get to your destination as quickly as possible. Don't take some very convoluted route. Take the shortest path to the destination. I'll point out, this routing is happening in the control plane of the network. And so really the function of our network is broken up into two pieces. We have the data plane and the control plane. And the data plane is the actual process of you get a packet, and you're going to look up and give it to a neighbor, the actual process of handling that packet. The control plane is making a decision of how you're going to handle that packet. So to which neighbor you should give for a particular destination, that sort of decision making is part of this control plane. So far we've been talking about link state and distance vector protocols as two of our approaches. I don't necessarily find link state easy, but I find distance vector harder because we start off with some general set of rules and we add these little optimizations to kind of make it function better and better. And so, especially because our project is focused on distance vector, let's talk about distance vector today and save link state for another time. So if we have time at the end, I'll take questions on that too. So what do we do for distance vector? It's two simple rules. One says every node is going to tell each of its neighbors its distance to some destination. Okay? Yeah, as a speaker. And so R1 is going to tell all of its neighbors, which here happens on the screen just happens to be R2, hey, my distance to D is 1. R3 is going to tell R2, hey, my distance to D is 15. By the way, where does that 15 come from? Well, maybe there's kind of a path off screen here, down below, through some more convoluted part of the network that eventually makes it back up to R1 and to D. And so as speakers, every node is going to tell all of its neighbors its distance to some destination. And then as a listener, every node takes in all these updates and decides which of them it should use, which advertisement it should use for its route. And that should be an easy decision. A cost of 1 to get to the destination is better than a cost of 15. And assuming that R2's cost to R1 and R2's cost to R3 are both the same, they're both 1, we should take the shorter route. What are some problems that we're going to run into? Well, generally, our problems in the network are caused by some sort of invalid network state. And so I'll actually turn to you and say, what are possible sources of invalid network state? What are issues that we can run into in the network? They're going to cause us to not route optimally. Yeah. Yes, we do have problems with links going down. I agree. And what's the result in the actual routing state? So in these tables that we've built, what happens? Yes. Yeah, I agree with that. You get state where someone thinks something exists when it doesn't exist anymore. And that'll be a problem. Someone else had their hand up, I thought. No? Okay. Any other problems you can think of? Yeah? Ah, yes, looping. So we can get into this unfortunate situation where both nodes think that the other has the shortest path to the destination. And then when they get a packet, they hand the packet to each other, and the packet goes back and forth. And that's a problem. I agree? Yeah. Yeah. Yes. And in particular, that does happen when we get some sort of kind of looping behavior where I tell you I have a path, then you tell me, no, I have a path, and we go back and forth until we count up. These are all problems that we'll run into, yes. This is great. So I've kind of written these down for us to walk through, and I framed them in these three groups. The first, I'll say missing entries, and what I mean by that is, no one really mentioned this, but for completeness sake, it is a slight problem if there does exist a theoretical path to some destination, but a router doesn't know about it, right? So there is some host that it's attached on the other side of the network, but I, as a router, don't have a path to it, even though it's theoretically reachable, and that's a problem. And we'll talk in a second about how that problem comes to exist. Then someone else mentioned loops, and this is exactly a problem. We can get into a situation where two routers think that they are each other's next best hop. But in that case, the packet's never going to make it. And that is a problem because we now have lost kind of, from that, starting from those nodes, you can't get to your destination. And finally, I think you mentioned this stale network information where not everyone knows about a failure that's happened. So, drilling into these missing entries, what might lead to this happening? If every router is following these two rules for distance vector we just talked about, and they're all honest, and so they're going to tell their neighbors what their distance is to destination, how would it be that not everyone knows? Any thoughts? Yeah. Right, right. So remember, we have this issue of our underlying network is delivering best effort. Some packets can get dropped. So you have this problem where you could tell your neighbor, but your neighbor might not hear it, not because they're ignoring you, but because the packet just doesn't make it. So that's definitely an issue. Advertising gets dropped. I have another one here for completeness, which I think is a little unfair. Just to say that maybe the destination is actually unreachable in your topology. Like a link goes down to some destination, or it's kind of not part of one overall connected component. And I just have it here for completeness. How do we solve this advertisement getting dropped issue? What was it? Yeah. As long as we resend every certain number of seconds, right? As long as our link is not always dropping packets, it has some % chance of making it, then if we just keep retrying, eventually the packet is going to make it. And so that works really well, actually. We just retransmit every X seconds. However, if the destination is unreachable, there's not really any fix for that. Whoops. Your only option is to get the network connected again, and so that's not really something we can fix with routing. So cool. This first problem, we have a solution for. We're going to retransmit advertisements. But what do we do about looping? This will be important.